Welcome to Module 7.1, Properties of Numbers. In this submodule, we'll discuss real numbers and various subsets thereof. We'll give the definition of integers, rational numbers, and irrational numbers. We'll then try to find good ways to identify them and study these concepts for the CLEP exam. We will focus on real numbers. That is to say, numbers that have no imaginary component. So recall that an imaginary number is one that includes the square root of -1 or I. And a complex number has a real part and an imaginary part. So it's something like z equals a plus bi, where a and b are real. Complex numbers and imaginary numbers are quite interesting, but at the moment we will restrict our case to real numbers. We will define several notions related to these. We should be familiar with many subsets of the real numbers, and we want to be able to identify them quickly for the CLEP exam. Let's begin. The first subset we will try to identify and study is what's called the integers. These are positive or negative numbers, including 0, that do not have a decimal part. These can be thought of as whole numbers, the numbers that you count with, together with negative numbers and 0. So numbers like -1, 0, 1, 2, and so on. And excluding numbers like 1/2, square root of 2, pi, anything with a non-trivial decimal expansion. The next class of numbers we want to be familiar with are what are called rational numbers. Where does this name rational come from? It comes from the fact that these are ratios or fractions of integers. So a rational number is a number that can be written as p over q for some integers p and q. In particular, every integer is also considered a rational number by just taking q to be 1. So we remark that p divided by 1 is equal to p. So every integer is also a rational number. Another point to make is that we have to be careful about our denominator. Remember that division by 0 is not permitted. It's considered an ill-defined operation. So we exclude the case q equals 0 when we consider rational numbers. Now, the discussion of counting rational numbers or putting them in a reasonable order is not something that's covered on the CLEP exam. But I do make a mention of it because it employs a really ingenious mathematical argument called Cantor's diagonal trick, or diagonalization argument. I just want to bring it up because I think it's good historical context. This was done in the 1870s, and is still, I think, quite beautiful mathematically. So if you find the idea of studying these different number systems, these different subsets of the real numbers to be interesting, I encourage you to read about Cantor's diagonal argument. There are many sort of basic expository articles available online, and a quick search engine search will help you find one. The last subset of numbers we will define precisely are those called irrational numbers. Unlike integers and rational numbers, in which a positive definition was given, irrational numbers are defined negatively. They're defined as not being something. An irrational number is any number that is not a rational number, that cannot be written as p over q for some choice of integers p and q. Right, so just to restate that, there are real numbers that may not be written as p over q for any integers p and q. These are called irrational. Now, even the question of do such numbers exist is not obvious. And in fact, this was confounding to the ancient Greeks. Pythagoras' school found this quite difficult to accept, or at least this is sort of the historical story. Maybe they were smarter than that. In reality, they realized these things do exist. But it's not so obvious to show that a number is irrational. It is certainly beyond the scope of this course. It's something that might be studied in a first-year course in proof-based mathematics at, say, the sophomore college level. Suffice it to say, some standard examples to know would be the square root of 2, pi. I'll also add e, and for example, things like square root of 3, square root of 5. In fact, the square root of most integers is not rational. So what characterizes these numbers? Well, they're interesting in that these are the numbers who have infinite decimal expansions with no repeats. You can have infinite decimal expansions for rational numbers. For example, 1/3 has the infinite decimal expansion 0.333 and so on. But it repeats. In fact, it repeats after one digit. Irrational numbers have infinitely long decimal expansions that have no repeats. They do not terminate and they do not repeat. Let's look at several examples of numbers and try to identify them as integer, rational, or irrational. Now, if we want to identify it as rational, we'll assume it's not also an integer. 2 plus square root of 2. Well, this involves a square root of 2, so it's suggested as irrational. Pi is, of course, an infinitely long decimal that does not repeat. It is irrational. The next one we'll look at is 17 divided by 4. This is the ratio of two integers and is not itself an integer. There's no way to simplify this to an integer. So this is a rational number. Next, we'll look at 12 divided by 6. Now, this looks like a rational number because it's the ratio of two integers. But 6 divides 12 cleanly. It's equal to 2. So this is actually an integer, not just a rational number. So we'll be as precise as possible and call it an integer. Another deceptive example is the next one, pi divided by 3 pi. We know that pi is irrational. But now I have two irrational numbers. Perhaps that is rational. And in this case it is, because the pi's cancel, and I just get 1/3. So this is actually a rational number. Our next example, square root of 49 plus square root of 64. I mentioned that most square roots of integers are irrational, but in this case we're being tricky. 49 is a perfect square, it's 7 squared, and 64 is a perfect square, it's 8 squared. So this is 7, and this is 8, so they sum together to get 15. So this is actually an integer. Next, we'll look at 121 divided by 11. Again, on the face, it looks like a rational but not integer. In fact, 121 is equal to 11 squared. So this is equal to 11, so it's an integer. Now we look at 16 divided by 3. This is the ratio of two integers. For example, negative 16 and 3. It does not come out cleanly. It is not equal to an integer. So therefore, it's a rational number. As our last example, we'll look at e to the 0th power. Now, e is an example of an irrational number. But e to the 0 is something simpler. Recall that a to the 0 is equal to 1 for all a. So this is equal to 1, and hence an integer. So when evaluating whether a given number is integer, rational, or irrational, one has to do all relevant simplifications to make sure that there's no hidden tricks we're not seeing. Let's do a few reviews. We would like to label the following statements as true or false. First, the statement is every rational number is an integer. Is that true? Can I come up with an example of a rational number which is not an integer? The answer is yes. For example, 1/2 is rational, but not an integer. So this is false. The second statement is there are integers that are irrational. Is that true? Can an integer be irrational? Well, no. Irrational numbers implies, by definition, not rational, which in particular implies not an integer, since all integers are considered rational. So this is false. The last statement I essentially just gave the answer away for. The statement is every integer is rational. This is true. All integers can be considered ratios of themselves and 1. So just by taking the denominator in a rational formulation to be 1. A last question is kind of tricky, and I just like this idea. We'll talk about what are called algebraic numbers. What are these? Algebraic numbers are those that are roots of polynomials with integer coefficients. I'd like you to give an example of a number that is irrational but is algebraic. That is, it is not the ratio of two numbers, but is the solution of a polynomial with integer coefficients. So the classic example here is square root of 2. I'll say it's known to be irrational, but it is a solution to the polynomial x squared minus 2 equals 0. So in fact, it is an algebraic number, even though it's irrational. Algebraic numbers generalize the notion of irrational numbers in the following way. So irrational numbers are numbers that are not roots of degree 1 polynomials. One can show this. The notion of algebraic numbers says, well, what if you are the root of any polynomial? Then I'll consider you to be good. I'll consider you to be algebraic. Are there numbers that are not the roots of any polynomials? That is, not only are they irrational, that is to say, not the root of an order 1 polynomial, but they're also not the root of an order 2, order 3, order 4, or any. They do exist, and they're called transcendental numbers. So these are numbers that are not algebraic. So not the roots of polynomials of any order. Some famous examples include pi and e. Showing that these are transcendental is quite difficult. This is a tricky exercise even for a skilled theoretical mathematician. But I think it is beautiful to know that people have studied how to go beyond irrationality and still found numbers that are quite confounding.